The silent wanderers exploring the realm of rogue planets. The cosmos, in its breathtaking vastness, constantly unveils phenomena that challenge our understanding of planetary formation and the very definition of a celestial body tethered to a stellar parent. Among these intriguing entities are the rogue planets, celestial nomads that drift through the interstellar void, unbound by the gravitational embrace of any star. These silent wanderers, once perhaps denizens of nascent solar systems or even born in the solitude of collapsing gas clouds, paint a compelling picture of the dynamic and often chaotic processes that sculpt the galactic landscape. Their existence, though only recently confirmed with growing certainty, opens up profound questions about the prevalence of planets beyond the familiar confines of star systems, the potential for unique environments far removed from stellar radiation, and even the faint possibility of life existing in the cold, dark expanses between the stars. The primary mechanism believed to be responsible for the genesis of these interstellar vagabonds is the turbulent dance of gravity within young planetary systems. During the early, crowded epochs of stellar and planetary birth, gravitational interactions between burgeoning planets, particularly the behemoths of gas giants, can become intensely disruptive. Close encounters or resonant orbital configurations can lead to a gravitational slingshot effect, flinging one or more planets out of the system entirely, casting them adrift into the galactic sea. The sheer scale of these early interactions, coupled with the potentially large number of planets formed in many star systems, suggests that the ejection of planetary bodies might be a relatively common occurrence, seeding the galaxy with a substantial population of these cosmic exiles. However, the narrative of rogue planet origins doesn't solely rely on ejection. Another intriguing possibility lies in their formation in isolation, mirroring the birth of stars but halting prematurely. Just as vast clouds of gas and dust collapse under their own gravity to ignite nuclear fusion and become stars, smaller condensations within these clouds might also coalesce. If these protostellar embryos fail to accumulate sufficient mass to trigger fusion, they could instead form free-floating planetary mass objects. These failed stars or sub-brown dwarfs, blurring the lines between the largest planets and the smallest stars, would then embark on their solitary journeys through the galaxy, never having experienced the warmth and light of a stellar parent. The very nature of rogue planets presents significant challenges to their detection. Unlike their stellar orbiting counterparts, they do not betray their presence through the periodic dimming of a host star as they transit across its face, nor do they exert a noticeable gravitational wobble on a central star that can be measured through precise radial velocity techniques. Instead, the primary tool in the hunt for these elusive wanderers is gravitational microlensing. This phenomenon occurs when a massive object, such as a rogue planet, passes directly between Earth and a distant background star. The gravity of the intervening object acts as a lens, bending and magnifying the light from the background star, causing a brief but distinct brightening. By carefully monitoring the light curves of millions of distant stars, astronomers can identify these fleeting microlensing events and, through careful analysis of their duration and shape, infer the presence and even the approximate mass of the unseen lensing object, potentially a rogue planet. The picture that emerges from these sparse but growing detections is one of a potentially vast and diverse population of rogue planets populating our galaxy. Estimates vary widely, but some theoretical models suggest that there could be billions or even trillions of these solitary worlds, perhaps outnumbering the stars themselves. This abundance, if confirmed, would dramatically alter our understanding of planetary demographics and the sheer quantity of planetary mass objects that roam the cosmos. These detected rogue planets exhibit a range of estimated masses, from smaller than Earth to several times the mass of Jupiter, hinting at the diverse formation and ejection processes that contribute to their existence. The environment experienced by a rogue planet is starkly different from that of a planet nestled within a star system. Bereft of stellar radiation, these worlds are plunged into perpetual darkness and subjected to frigid temperatures approaching absolute zero. Their surfaces, if they possess any solid ground, are likely to be covered in thick layers of ice, formed from the freezing of any volatile compounds present. The primary source of heat for a rogue planet would be its internal geothermal activity, generated by the slow decay of radioactive elements within its core and the residual heat from its formation. This internal warmth, though significantly less than the energy received from a star, could potentially sustain subsurface liquid water oceans in some larger rogue planets, particularly if they possess a sufficiently dense atmosphere to act as an insulating blanket. The tantalizing prospect of subsurface liquid water on rogue planets raises profound questions about the potential for life beyond the traditional habitable zones of stars. While the lack of sunlight would preclude photosynthesis as we know it, the possibility of chemosynthetic life, thriving on energy derived from chemical reactions at hydrothermal vents on the ocean floor, cannot be entirely dismissed. Such life would be independent of stellar energy, drawing sustenance from the planet's internal geological processes. While the conditions would undoubtedly be extreme and vastly different from those on Earth, the sheer number of potential rogue planets in the galaxy suggests that even if the probability of life arising on any single one is infinitesimally small, the sheer volume could make the existence of such life a non-negligible possibility. Furthermore, the study of rogue planets offers a unique perspective on atmospheric science and planetary evolution in the absence of stellar influence. Some rogue planets, particularly those with significant mass, might retain substantial atmospheres, possibly composed of hydrogen, helium, or heavier molecules depending on their formation history and subsequent outgassing. These atmospheres, shielded from the stripping effects of stellar winds and radiation, could potentially exhibit unique chemical compositions and dynamic processes driven by internal heat and planetary rotation. Studying these atmospheres could provide valuable insights into the long-term evolution of planetary atmospheres in isolation. In conclusion, rogue planets represent a fascinating and increasingly important frontier in our exploration of the cosmos. These solitary wanderers, ejected from their stellar cradles or born in the darkness between stars, challenge our conventional understanding of planetary systems and the conditions necessary for planetary formation and even the potential for life. As our detection techniques become more refined and our theoretical models more sophisticated, we are beginning to glimpse the true extent and diversity of this hidden population of celestial bodies. The silent journeys of these interstellar nomads offer a profound reminder of the dynamic and often unexpected nature of the universe, constantly pushing the boundaries of our knowledge and igniting our imagination about the myriad possibilities that lie beyond the familiar glow of distant suns. The exploration of rogue planets is not just a quest to count the lonely worlds adrift in the galaxy. It is a deeper inquiry into the fundamental processes that shape the cosmos and the potential for life to exist in the most unexpected and challenging environments.